Okay, thank you very much for the introduction and welcome to my presentation. As already mentioned, this is joint work with Erich Teppan and Dietmar Jannach. And this work deals with job shop scheduling, which is an important NP-hard problem in today's industries. Constraint programming is one promising approach to solve the GSSP problem and has a long and successful history and can handle large-scale GSSP instances. However, modern production regimes are often highly dynamic and can lead to computationally hard optimization problems on top of this GSSP problem. One typical such problem is that we have a number of jobs that exceeds the production capacities, and our goal is then to find a job set of maximal utility that can be finished before a given deadline. This is what we call the job set optimization problem. The JOP can be solved by standard CP solvers by suitably adapting the given GSSP encoding, as is shown in the animation at the bottom. However, even cutting-edge solvers are having problems with the increased complexity of the JOP problem. Let me now briefly introduce the problems we are considering in this work by means of examples. First, we have the GSSP, which you all might be familiar with already, where we have given a set of machines, a set of jobs, where each job consists of an ordered sequence of operations of particular length, and each operation has to be performed on one particular machine as indicated by the colors in the example. And the goal is then to find a schedule which maps each operation to a starting time on its respective machine, such that the overall completion time is minimized. In our example, one solution would be given by this schedule here, which has a completion time of 9. And we can also define a decision version of this problem where we have a deadline k given, and we ask the question if there is a schedule that can finish all the jobs before this deadline. In this case, this would be a negative instance because not all jobs can be finished before time point 6. Then we have the job set optimization problem, which assumes given a GSSP problem instance, as we have seen on the last slide, along with a deadline and with a utility assigned to each of the jobs, where in this particular example, we assume uniform utilities. And we then search for a job set to be eliminated such that the remaining jobs can be scheduled in time and have a maximum utility. So one solution to this problem would be to eliminate job number 4. This would lead to this schedule here. And we can also think of a relaxed version of this problem. So we can simply replace this utility optimality criterion by a subset minimality criterion. And we would find that the solution presented below is in this case also a solution to this relaxed job set maximization problem, as we call it. And another possible solution would be to eliminate job 1 and job 3. This would look like this. However, this would not be a JOP solution any longer. Now, our approach is based on 4 observations. So the first one is that each JOP solution is also a JMP solution. So this is illustrated by this little picture here. And second, that JMP has a lower complexity than JOP because the JOP solutions can be intuitively regarded as the best JMP solutions. So it requires us to solve one NP-hard optimization problem to come up with a JOP solution. On the other hand, for JMP, we have efficient algorithms which require only a linear number of calls to a GSSP decision oracle. So computing JMP solutions is more efficient. And the last observation is that CP solvers typically do not support direct JMP solving. So our idea was then to try to approach JOP by drawing a random sample in the JMP solution space. So in a nutshell, the procedure involves solving multiple randomly modified JMP instances and to store the solution with the best utility throughout the process and to terminate if desired solution quality is achieved. This approach is illustrated by this picture here, where we have 3 modules. The first one is a CP solver, second one is a JMP unit, and the third one is a random number generator. And the JOP instance is first forwarded to a problem instance modifier, which randomly modifies the problem instance and feeds it into a search algorithm, which communicates with a CP solver, and in this vein generates, so to say, a random sample of JMP solutions, where we store the best solutions with respect to utility throughout the process. So the main rationale is to solve the implicit subset minimality problem in JOP explicitly, and in this vein to trade one hard optimization for multiple easier decisions. And this approach has several favorable properties. First, we have no information exchange that is necessary between the different GMP computations, which allows us to efficiently parallelize this approach. Then we have no additional human interaction that is required, and all modules are viewed as black boxes, so we can instantiate them by the most suitable algorithms for a particular problem. We evaluated this approach by means of 100 JOP instances of different types and using 5 degrees of over-constraintness. And the experiments involved a comparison of the direct CP approach, which we discussed in the first slide, with the proposed indirect approach, where we instantiated the modules in terms of the CP solver. We used IBM CP Optimizer, which is currently a state-of-the-art CP solver for JSSP. And for the indirect approach, we used inverse quick explain as a JMP algorithm. Moreover, we had 2 different computation timeouts of 1 hour and 2 hours. And the results showed that for both timeouts and all JOP instances, the proposed technique led to a higher number of scheduled jobs than the direct CP approach. And even the proposed approach yielded better results within 1 hour than the direct approach within 2 hours. So we both have a time and a quality improvement that we observed. And the quality improvement amounted to up to 15% for the left instances and up to 13% for the right instances. Thank you for listening, and I'm happy to take questions now.